Good morning. So this is our 750 economic growth, and this is our last lecture. And today, what we're going to discuss is mainly automation and the types of technological progress, uh, that replaces labor and so on. So I have some set of slides. So what I will do is not to go into every detail of these papers. So there are basically three papers that I want to touch upon. One is that very nice paper about automation, written by Agion, Jones and Jones. I think this was published in a book as a chapter. Then there is also this other paper on factor eliminating technological change by Pareto and Seater. And I also want to show you some of the fundamentals of the task-based framework of Daron Acemoğlu and David Autor. Okay. Then, since it is related with that, I will show you a very simple model of capital versus innovation, right? Because there's so historically speaking, capital accumulation was a more dominant feature of long-run growth. I mean, more important determinant of long-run growth rates, for instance. But in the advanced stages of capitalist development, innovation takes a perhaps more important stage. So I want to show you a simple model where there's both capital accumulation and innovation that depends on R&D investments. Okay. So let's start with the first paper. So here we have some tasks. Okay, so there is this output Y. Okay, so this output is produced by a number of tasks. Okay, so if you accomplish a number of tasks, here these tasks are denoted by X's. All right, then you have your output. So how can this be interpreted? For instance, there is the task of production. There is the task of so when you see the final output, production in the largest sense includes the management of the firm, the transportation of the goods, the marketing activities, or the other commercial activities, and so on and so forth, right? So there are many different tasks a firm should accomplish at the until the final stage of the production activity. Okay, so each of these tasks in this very simple model by Zera can be accomplished in two ways. One is that you can use human labor, L, right? In that case, if you are using only human labor for task I, we call this non-automation or not automated task. Okay. Otherwise, you can find it optimal to use capital stock or robots, all right, industrial robots for some of the tasks. And in that case, we call it automation, right? So if you use machines, or if you use robot labor for a task, then this task is supposed to be is called to be automated. Okay. Now here in this particular framework, the tasks have this Cobb-Douglas shape, right? So there is unit elasticity of substitution between the tasks, and there is also constant returns. So if you have a larger success, for instance, in all of these tasks, then your production is to be larger. Okay. Now, if you extend the notion of allocation of resources within the firm, right? You may imagine that, okay, this firm will allocate capital and labor into different tasks, right? So think about this in terms of, in a general setup. So some of the tasks, depending on these alphas, obviously, right, and the factor prices, will be allocated to, some of the tasks will be delegated to human labor. Some of the tasks will be delegated to robot labor. So in that particular sense, we can think of aggregate notions of capital and labor at the firm level, right? So suppose that this set A, here you have a calligraphic A, is the collection of tasks that are automated, right? And N is the set of the tasks that are not automated. Okay. Now, if that's the case, these products, right, can give us some aggregate index of capital or the robot labor at the firm level, and some aggregate index of human labor again at the firm level, right? And then, of course, you can go from this definition to some sort of a Cobb-Douglas form. All right. So if you look at this paper, Agion, Jones and Jones, they actually pursue that idea a little bit further. But instead, what I will show you, again from the same paper, is a more tractable and more general way of doing that. Okay. Now it is more tractable because we use an integral here. So there is an infinite number of tasks, right? Again, x's are denoting the tasks that the firm needs to accomplish or to complete for production, right? And it is more general. Why? Because we allow for elastic substitution that is different than unity. Okay, so here when rho is less than 0, this is the CS type, as you know, right? So if rho is less than 0, these tasks are complements. Okay, and in fact, if rho goes to the negative infinity, as you know, again, these tasks are perfectly complementary, right? But now I'm just saying that rho is negative, so there is complementarity between the tasks, which makes a lot of sense for the real firm, for the real world firms, because they have to accomplish the production activity first. They have to transport the raw materials. They have to transport their workers, their other type of stuff they have to use, and then they have to organize a production. Then they have the marketing activity, right, and so on and so on. So these are complementary to some extent. If rho is less than 0, then the elastic substitution is less than 1, so they become complementary tasks. What we also assume here is that there is some sort of technological progress. All right. So for simplicity in this lecture, I'm going to assume that, as in the paper, I'm going to assume that this is fixed, right? So G is fixed and exogenous. So we don't really want to deal with it right now. But as you know, we have a number of theories, different theories that we can use to explain how can this technological progress takes place endogenously, right? So right now we are not going to do that because we want to focus our attention on automation. Now, once again, a task can be performed by human labor or by robot labor, right? So if human labor is used for a task, then this task is not automated. If some sort of an industrial robot or a machine is used, then it's automated. Okay. Now, how can we go from this firm level stuff to a macro model, right? So, well, this is exactly as in the solo model, the simplest model you may imagine. So there's consumption expenditure, there's investment expenditure. These two must sum to output, right? Because that's the income. So the economy is closed, there's no government. Then there's capital accumulation equation, right? So if there's investment expenditure that is equal to IT, and the existing capital stock depreciated at some fixed rate delta, so then IT minus delta KT is the net increase in the capital stock. And then these are the labor market and capital market equilibrium conditions, right? So the total labor endowment LT must be allocated to all of these tasks. So some of, it is used for some of these tasks, but in total, the total demand by the firms must be equal to total supply. The same is true for capital stock or the machines. So if you think of this, in any point in time, there will be some tasks, right, that have been automated. So we denote this share, okay, by beta t. So beta t is a number between 0 and 1. So at each t, you may imagine that time is discrete or continuous. I think, okay, so this is continuous time here. We already assumed that. So beta t is the fraction of tasks that have been automated as of t, right? And if that's the case, the total capital stock, and if the market clears for both capital and labor, so then you can write the production in this way. Okay, so you can actually show me algebraically that this must be true, right? From this to this equation, okay? Because that's the capital stock per task, right? And that's the labor employment per task, okay? And the fraction beta t of the tasks are automated, so it is that part, and the remaining fraction 1 minus beta t is non-automated. Okay. Then after some arrangements, you have this, right? Because this is 1 minus beta t as well. Then from this, you can write factor income shares. Okay. Now, why factor income shares are important here? Well, because when we think of automation as graph economists, most of the time our interest lies in understanding inequality, right? Especially after 80s. So there is this increasing inequality within different, among workers of different education classes, right? So high school graduates earn some wage, college graduates earn some wage on average, of course. And if you look at the difference between these average wages, average earnings, you see some difference, right? So increasing inequality in favor of college graduates. So how can we, for instance, understand that? Or if you look at the total payments for capital services in the economy versus total payment for labor services. So if this is important, then we should look at this ratio, right? So alpha KT is the factor income share for capital, and alpha LT is the factor income share for labor, right? So how do we write that? Well, under competitive conditions, the factor price, right, will be equal to this derivative, right? If perfect competition prevails, then factor price of this machine will be equal to that derivative. And then we also have total capital employed, and we have the income, right? So so you may imagine that this is R. So R times K divided by Y is the factor income share. And similarly, this derivative gives you some definition of real wage, obviously, right? Because under competitive conditions, again, firms maximize their profit by choosing an optimal amount of labor. So this gives you the wage in a sense, and W, so you may imagine that this is W times L is a total wage bill, right, in the economy, and this is divided by total income, gives you the factor income share for labor. So then you look at the difference between factor income shares, right? So the difference between capital income share and the labor income share. Now that ratio is governed by two variables, as you see. One is beta, and the other is capital stock per worker. So from this, you take the derivatives, you define these alpha K and alpha L, then you realize that this ratio satisfies this equation. Okay, so you can actually do it. So then we should ask, so how can we understand the changes in the ratio of capital income share to labor income share, right? Because in the data after 80s, okay, at least in many developed countries and in many developing countries alike, so that ratio is actually increasing. Okay, so you know, the income share obtained by the capitalist class, so to speak, relative to the income share of laborers is actually increasing, right? So how do we increase? How do you understand the increase in this ratio? Well, one reason could be the increase in beta T, right? So if there is automation, okay, if more and more tasks are automated, that creates an increase in the relative share of capital income in the economy. Okay, as you see from this, in fact the effect is nonlinear, right? So if you have one unit increase in beta, the numerator increases, but also the denominator decreases. So the effect is nonlinear, and it also depends on, of course, how strongly complementary these factors. Right? Because if Rho is getting larger and larger in absolute value, this exponent is getting bigger and bigger since Rho is negative, right? So automation then is an important determinant of income inequality, all right, in the economy. Even if we look at the functional income inequality as in here, right? So here we assume that all the capital owners are alike and all the labor owners are alike, right? So imagine that there are two classes. So then one class is getting better off, is benefiting in terms of income from automation. Now the other reason would be the decrease in K over L. Okay, so if Rho is negative, right, we can understand the increase in the capital income share relative to the labor income by the decreasing capital stock per worker. But this is not true in the reality, right? In the data, we also see that this is increasing. So what does this suggest? If tasks are complements, if Rho is negative, then automation must be really fast after at least 80s or 90s, at least, to imply an increasing ratio of alpha K to alpha L. Okay, because we observe in these capitalist economies that K over L is increasing, right? So there is capital accumulation continuing in these economies. So that means that increase, by increasing the relative supply of capital, must decrease the relative price of capital, obviously, right? So it is a fact. It's an effect that runs counter, on the opposite direction. But then since we observe that alpha KT divided by alpha LT is growing faster after 80s until present, then we must conclude within this model, we must conclude that beta increase, the increase in the part that is due to automation must be rather fast. Okay, so the first term here dominates the second term because KT over LT is increasing in the data. All right. Now, of course, these conclusions will be reversed if tasks are substitutes, right? So if rho is positive, if the elasticity of substitution is larger than 1, then you would have what? You would have the opposite effects, right? So here, an increase in the relative supply of capital would be actually better for the capital owners, okay? And in terms of automation, it depends on whether rho is, greater than 1 or not. So if they are gross substitutes, if rho is positive and larger than 1, right? So this number will be negative. So if rho is so there is this intermediate, there's this interval where rho takes values between 0 and 1. So in that case, automation is still benefiting the capital owners. But if rho is larger than 1, if the tasks are gross substitutes, then actually rho cannot be greater than 1. I'm sorry. Sorry. So I was confused with the elastic substitution. So if rho is equal to 1, actually, right? So So if rho is equal to 1, the production function is linear actually. So they become perfect substitutes, okay? And the automation has no effect, right? With rho is equal to 1. But if rho is sufficiently large, sufficiently close to 1, then these tasks becoming increasingly more substitutable, right? So then the effect of automation decreases. So that is one important lesson then, right? So when we think of large firms that have many different tasks to accomplish to complete the production cycle, including management, transportation, the production activity itself, and so on. And if these tasks are complements, at least the LSO substitution is less than 1, even slightly. We see that automation has a very important role in explaining the movements of the capital income share, and it dominates the effect of capital accumulation, right? Because again, the simple neoclassical argument dictates that if something is supplied more, relative to some other thing, right, the relative price should decrease, right? But that's not happening. Why? Well, most possibly because of a more complicated story about automation in the real world. So as you see, this is much more realistic and much more general than the simple Douglas production technology we always use. So it is important to understand such differences. Now, I want to also show you a figure from this paper. So this figure is from Agü and Jones, and that shows you a particular simulation of the model. Okay, so in that simulation, so the blue figure is the growth rate of GDP over time. Okay, so suppose that there is, so we already assume that this continues, right? So AT is getting larger and larger, but in terms of GDP per, so the growth rate of GDP over time, of course, depends on, how fast capital accumulates as well, right? So here at these dates, when you see the jump, there is a change in automation. Okay, so we start with at time 0, we start with beta equal to 0.4 and capital share of income being equal to 0.2. Okay, then what happens? Automation increases, okay, until like the first, and at the end of first 30 years, and that increases as you see the capital income share, right? Then automation stops for some time. Here beta is exogenous, all right? Automation stops for some time, and in that episode, the GDP per capita, so the GDP growth rate is lower, all right? Then automation continues again after some time. Then capital income share increases again, and then growth is faster, all right? So as you see, there could be a move from lower levels of automation to higher levels of automation, okay? And when that continues, depending on the other determinants within the model, of course, we could see a capital share change, such as this one, all right? And a fluctuation in the growth rates, okay? So in fact, if you look at the growth rate data for advanced capitalist economies, you would see such sorry, you would see such fluctuations. Okay, we have now 10 minutes. So this again is a stochastic simulation of the model, but beta is exogenous. So here authors determine how beta changes in time, and as you see, there are cycles of automation. So there's an automation cycle for 30 years, about 25 or 30 years, automation continues, then stops for another 25 or 30 years, then continues again at some pace through 35 years. And that goes on like this. And depending on GDP and labor and all the stuff, you would see a trend of inverted U shape for capital share and some wild fluctuations in the growth rate. Okay, now let me stop here before discussing the factor elementing technique change. So now if you have questions, you can ask and we can discuss them, or if you have comments to share.
Professor.
Yeah, go ahead.
I wonder, in the first slide or second slide, we are seeing that we can imagine a product and LE if the task EI is not automated or automated, but we think the reality actually, we consider the automotive production, and there are 70% robots and 30% labor. But there is a strict distinction here. Our product should be totally automated or not automated. Am I right?
Well, not the product, but the task, right? So the product here is Y, right? So this is the automobile, right? So the car is here. Then there are different tasks. One task is the, let's say, transportation of raw materials,
yeah, I see.
right?
Okay, I got it.
But then of course you are still right. So some parts of this. So here we are assuming a binary allocation. Okay. Yeah. So either you're gonna use labor for the entire job, or you're gonna use robot for the entire job. That must not be the case in a more general setup where some of the tasks, so you can still use both of them for the same task. But that requires, of course, a particular relative price, right? So factor prices must be in balance given the productivity levels. Okay, so here I'm showing you that one unit of human labor is exactly productive, is as productive as 1 unit of robot labor, right? So what determines the allocation here is totally the elasticity and the factor price. So you will see, just be a little bit patient when we look at the Acemoglu and author's paper. You're going to see a much more satisfactory explanation in the next hour.
Okay, thank you.
So here it is binary, yes, either capital or labor. Any other questions or comments? Okay, now you can actually write this write this in Excel or in MATLAB to obtain this figure. Okay, so if you want to play with it, just use this equation. You can just use this equation or these equations as well, of course, right? So suppose that beta changes, so you will have one column of data for beta, right? So beta will be changing from year to year. Then you can calculate all the other stuff, all the other endogenous variables, and you can actually draw a figure like this. So that would be a nice exercise. Okay, I'm gonna switch now to Pareto and Seiter's paper, but let's take a break because I don't want it to be interrupted later on. So my time is about 9:40. So let's meet at 9:55, all right, to continue our session.
Okay.
All right, so let's meet at about 15 minutes. Bye-bye.